This is the landing page at beta.cerepo.com. Here we have a folder-like structure. I'm going to look in light source facilities, and then I'm going to look at NSLS-II, and then we're going to look at the coherent hard X-ray beamline, CHX. Here you see two simulations, one with a conventional or idealized undulator representation and one with a more realistic tabulated undulator representation. I can open this simulation, or I can create a copy or other things. Here I'm going to create a copy. I'm going to give it a name, my CHX 01, create the copy, and then we go right into the simulation. This is the source page where the undulator is specified as well as the electron beam. And it makes a series of plots for you. Electron trajectory will appear here in the lower right. The intensity, 20 meters from the undulator. The power density. Here, the on-axis spectrum. This is all at 9 keV. You can click near any of these peaks and you can see information about the plot at that location, and it will automatically find the peak for you so you can see the different modes. You can zoom in and out by scrolling the mouse. Here we go to the beamline tab. Here you see the sequence of elements laid out. A slit, a couple more slits, a compound refracting lens. HDM is a horizontal deflecting mirror, a focusing lens, another slit, and then a watch point, which is where the sample is located. Here it's calculating automatically for you the initial intensity at the beginning of the beamline, and then it's propagating the wavefronts through the beamline right now, and when it's done, it will show you the result here. I'm going to quick jump over. This is a fully coherent simulation. On this sub-tab, I'm going to quick jump over to the partially coherent tab, and I'm going to start that simulation. That takes longer because it essentially repeats the coherent simulation multiple times with different phases to give you an accurate representation of a partially coherent wave propagation, but it takes longer. So if we go back to the coherent one, this is still running. There it's finished, so you can see that the X-ray pulse has been focused down. You can zoom in and out with the mouse, drag back and forth here. If you click, it zooms onto the data point, and then it tells you the values up here of the horizontal and vertical along this axis or along this line out. You can do the same thing. With your mouse, you can scroll back and forth to get the data at exactly the number that you want. Here, we can modify any of these elements. Here's the slit with a rather simple element name, position, whether it's rectangular or circular, the horizontal deflecting mirror. You can specify mirror errors if you like, or you can leave it as an idealized mirror. More slits. Here's the compound refracting lens, which has quite a bit more data that you can specify. And here's a simple lens. And then the watch points can be put anywhere. You're just going to get to see the beam intensity wherever you place a watch point. And of course, the final watch point is where you would imagine the sample to be. You can also drag down more elements. If you were going to put a mask here, you could then specify the location of the mask and its other properties. I don't really want to do that, so I'm going to delete it. and we're going to cancel all the changes that we made here. Now we're going to go back to the partially coherent tab and see what's been happening. It's been running for 2 minutes, and this is what the partially coherent intensity looks like at the sample so far. This just keeps running and statistically sampling the phase space associated with the electron beam emittance and energy spread until it appears to have converged, and then you can click End Simulation down here. I'll go ahead and do that now. So when you're done with the simulation, you can go up here to this cogwheel. The cogwheel always offers you a series of more sophisticated user controls. You can change the initial wavefront simulation grid. By default, it makes choices automatically, which is the best choice to make. It's propagating a 9 keV wavefront. If you change the properties of the undulator or the electron beam energy, the resonant energy is going to change, and you'll want to change this number. You can specify a documentation URL. Here I'll put in the RadiaSoft web page. Save the changes. Once I've done that, then now this notes icon has appeared. It wasn't there before. If I click on that, it takes me to the RadiaSoft web page. So that's where you might have some detailed description of your beamline that would be useful for you or users or collaborators to see. You can also export this simulation as a Python code. Here you see a valid Python script for running SRW. You can also export as JSON data file. JSON is just a simple Python data format in plain text, and here you can just see, without all the Python code around it, just all of the essential parameters which are used to define the simulation. And you can import these files into the GUI and start up a new simulation in that way. And so I'm going to go back to simulations here. Here you see my copy. I can create a new folder called Demo, save the changes. I can now move this into the demo directory. We go to there, move, and now it's in there. And we'll stop here.